Okay, we'll start with the uh, famous architecture. So as I said, when this convolution neural net started to come, is there was this ImageNet challenge which was having this uh, very big data set and a task to improve that, and every uh, artificial intelligence practitioners or the deep learning practitioners were focusing on improving accuracy in the image classification challenge. So it all started with image classification, and this was a very standard challenge that everyone struggled at that time. So it was a very common thing to do. So then this was the first architecture in the ImageNet challenge that used a convolutional neural network, and also it used GPUs for training this thing, right? And also this is the architecture that introduced the use of ReLU activations, and it won the challenge, right? GPU parallelism, this is the architecture that introduced. Right? So the basic idea is using different filters that you can see here. It's just an architecture that you can see. Usually, when you're designing a convolutional neural network, what we usually do is uh, we extract, like, we use different filter sizes, right? So initial layers will have large filter sizes, and the subsequent layers will have reduced filter sizes. So here, the idea that is used is 11, 5, and then 3. You can think it like that. And then in between that, every 3 cross 3 thing will be there. So 11, 3, 5, 3, and then 3, 3, and again 3, 3. So these kind of blocks will be there. And also as the layers go deep, you increase the number of uh, kernels that are used, right? So that is also there. So here the number of kernels is 96. So this block that you are seeing here is not actually kernels that you have to think about. Uh, uh, this is not the kernel. This is the feature map. These are the kernel sizes, right? Okay. So now let's talk about one small detail in this kernels, right? So as I said, how the convolution works, right? You have seen images; it goes in this direction like this, right? So assume I am using a 3 cross 3 kernel here, right? In this RBG image. How many parameters will that convolution kernel have, including weights and biases? I won't say that. If it is a 3 cross 3 kernel and input is an RBG image with 3 channels, what will be the number of parameters? Assume we are having only one 3 cross 3 uh, kernel. Okay. So here there are like 96 kernels and the output size is 55 into 96. But if we are using one 3 cross 3 kernel, in that layer, how many parameters will be there?
So 27.
How?
So 3 cross 3. So 9. And because there are 3 channels for each. So 9 into 3. Or will it be 9
Okay,
plus 3?
9 into 3 is fine, but we should also add the biases to it, right?
Bias yes and
So,
plus 1. 20.
so 28 the thing will be there. Now let's do the same thing for this actual layer. Let's see, find out how many parameters are there in this convolutional layer. So there is 3 cross 3, right? Total parameters. So we talked about just one convolutional kernel, but here in this layer, I think you can see the numbers, right? So this is the 3 cross 3 convolutional layer, and the output size is 256, right? So how do you compute the number of parameters in this particular layer? Any idea?
It will be be 27 minus kernel size, which will be 3. So it will be 24 divided by the stride, which will be 2. So 24 by 2.
Oh, number of parameters. I am asking about the number of parameters in this layer.
Oh, okay,
So
okay.
stride doesn't affect the number of parameters.
Okay, so then it
That
will,
will affect the output size.
So input size dot output size
yeah, output times input, the
or
matrix.
plus I will and addition of output
Mm,
size.
not really. So, okay, let me clear this up.
Mhm.
So here we are talking about the number of parameters. So, which means the number of uh, elements present in this convolutional kernel. So, take one kernel. So, what will be the size of one kernel in this? When what we are doing is we are doing striding over this. Okay, and first take one kernel. This is our input size, right? Okay, so with this input size, we are not going to have 27 plus 27, but one convolutional kernel will have 3 cross 3 into 256 elements. It will be a 3D kernel, but moving in two directions, right? So there will be 3 cross 3 times 256 elements, right, in the kernel. With biases, it will be plus 1.
Sir, how did we get to 56?
So here there are like two. So as you said, I think here your convolutional kernel is 3 cross 3 and times 3, right? For all those channels. One convolutional kernel will also span to the depth. And we move that kernel in this like in a 2D direction. We go sideways and then come downwards and we stride it like that. But the kernel itself will stand for all channels, one convolutional kernel. Because in one convolution kernel, we don't only stride with this one image and take the output. We stride with all those images and do the output. So basically, when doing convolution, it's not a 2D image that we are convolving. So we are convolving with a 3D block of kernel, but it will move in 2D direction. So for example, in this one, assume here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it will be like this, right? So in a 2D convolution with one image, you dot product all these values and put it in this value, right? Enter value. Similarly, when you do with a 3D input, when you do 2D convolution with a 3D input, you move in 2D direction. So you will have this block. So in for one value, you will be doing a weighted sum of all these 27 values, 1, 2, 3, 27, and that will give you one value, right? And we need, so this is one kernel. So one kernel will have, in this case, we are using 11 by 11 kernel, right? So here it would have how many parameters in that case? It will have 11 cross 11 times 3 plus 1 parameters. And this is for one convolutional kernel. So if we have to identify the whole parameters in this one layer, this one layer also has 96 kernels, such kernels. So this is the number of parameters in one kernel in this layer, right? So if we have 96 such kernels, the total number of parameters in this particular layer is this. If you are writing this using a formula, if you say the kernel size is k or okay k, so our number of convolutional parameters would be k cross k times the input size or the input depth you can call. Depth plus 1 or in channels we can denote it with C in. C in. So the number of input channels times the number of output channels. So this will be the number of parameters in this whole layer, right? Did you get that part? How this 2D convolution that we are doing is, yeah.
So why is there uh, there's only one bias for every single channel? Like there's a common bias for should there not be three biases
So
when
there
we
are
do like
actually
11 times
96
11?
biases. There are actually 96 biases in this whole layer. For each of this feature map, you will have one bias.
Oh, yeah. Right. Okay.
Okay. But for each kernel, so each kernel will produce one feature map, right? Each kernel after convolutional will produce one of these images. Okay. Okay. Yeah. So that's what happens when you convolve here also. So here, what will be the number of parameters over here? It is 3 cross 3 into 256. So that number of one convolution, we have to take the sum of 3 cross 3 into 256 values to produce one first pixel over here. To get this first pixel over the first image, we need to take all these values. So this whole thing we have to take, right? Okay. Just a minute. Yeah. Hello, am I audible?
Yes.
Okay. So I hope that part is clear. Okay. Okay. So now let's see this one. So as you compute this one, let's see what is the number of values that are present there. Okay. Let's compute this value. So this is from 30,000. And let's see how much parameters are there in this one, this layer. This would be 3 cross 3 into 256 times 1 times 256. The parameters is increasing. Let's also see how many parameters are there in this fully connected layer, right? So this is the number of parameters that are present in that convolution layer. Let's see how many parameters are there in this fully connected layer. 9216 times 4096. You see the number of parameters in this layer is very large. So usually in a convolutional neural network, the fully connected part will have more parameters than the convolutional part. So usually this convolutional part works as a kind of feature extractor, uh, it detecting features from like localized features from each image, and then in the final we flatten it and then use a fully connected network to compute the things. Okay, so this is how a basic convolutional architecture will look like. You can design a similar convolutional architecture by using a bigger filter. So this is, and then reducing the filter sizes, the kernel sizes, and then increasing the number of filters, and then flattening it at one point, and then doing it. So based on the input image size, you can design your convolutional architecture, right? So that is one thing, one basic thing you have to know about constructing it. And then there came this VGG net. So here the major idea is using, so here as you can see here 3 plus 3 kernels are used alternatively, but here the same kind of kernel are used, and then one kind of pooling layer is used. So this introduces the use of pooling layers. As you see here there are no pooling layers that are used, but here to reduce size, so here size reduction is done by convolutional itself with the striding difference in striding that you can see, that's how the size is being reduced. But here this architecture introduces pooling layer to explicitly reduce the size and then do a convolution with layers. So that's how this uses, and it uses 3 cross 3 filaments, right? And that is it. So it has fewer parameters by design. So that is one thing about the VGG16 architecture. And then ResNets introduce a concept of residual connections, which means uh, the idea is this. So the input passes through one layer and it goes to another layer and comes here. But we can use this input also as a feature. So this is a kind of higher level feature I extracted, but this is a raw feature. Sometimes we can also use these both features together to this layer, right? So this layer, so this signal can also pass through this. So the main idea is to solve the degradation thing. So sometimes when we propagate weight backwards, it may not propagate uh, properly because it has to pass through many layers. But with residual connections, when we back propagate, it can pass to back, the gradients can pass backwards easily. That is one advantage over this. So this is the skip connection architecture that's introduced in this ResNet, right? And then the other things are like the layers and the pooling is also there in this one. So this is the key. So what are the, you should remember, well, when learning this architecture, we should remember the key change that is introduced in this architecture, right? Here it introduces ReLU and uses convolution, basic convolution architecture. So this is how a basic convolution architecture will look like. And then it introduces pooling layer to reduce the number of parameters, right? And also the fully connected layers are also uses ReLU here, right? And then the ResNet introduces residual blocks or skip connections. That is the important thing that to remember in residual thing. In GoogleNet, it introduces something called the inception module. So let's see about inception module, right? So one idea is all these previous architectures are using one in a particular layer. It is using only one type of filter, right? One size of filter. But this ResNet inception module introduces three parallel convolutions, which means you are convoluting the same image with three different filter sizes and concatenating the output and doing that, right? So let's see the architecture over here. This is how a inception module look like. You perform, so first you perform one cross one convolution also before going to this one. So what this one cross one convolution does? Any idea? What is one cross one convolution does?
Nothing, right?
No, no, it actually does something. So if you see, this relates to the one thing that I talked about. So when you do convolution here, as
It's
in
a
we are
great
using a
gem.
one cross one. We are using one
Very
cross
small
convolution.
details. It takes minute details, localized
No, no,
details.
no. Okay, so okay, let's see how a one cross one convolution look like, right?
Yeah.
So as I said, as in you are using a one cross one convolution in this one, what will be the size of the convolution kernel? 1 cross 1 into 256, right? 1 cross 1 into 256. That will be the size of the convolution kernel. So basically, we are not taking information in like parallel information from one image, but we are taking we are doing a dot product or a weighted sum over all the channels. Okay, so the usual convolution also takes everything over the channel, but it also looks into the neighborhood in one single channel. But in a one cross one convolution, it won't look at the adjacent pixels of a single channel, but it will look the same pixel of all the channels. It's like we are connecting a fully connected layer over each of this one and connecting that to the particular point. So this particular first point will be connected to all of these edge pixels. You can think it of like that, right? It will be a weighted sum of all of these first pixels in all the channels. This first pixel here will be a weighted sum of all of these pixels. So we are essentially kind of learning dependencies between the channels.
Sir,
So, right?
sir, what activation function we are using in this one cross one?
You can use ReLU, whatever activation function that doesn't
So my
affect you. Yeah.
so sir, my question is the three channels. Let's say per channel, the pixel value is uh, 200, 200, and 200. So the ultimate
Okay.
value that the convolution will give is 600. So
No, no, that depends upon the weights, right? The convolutional kernel will also have weights associated with, right? It won't be one. It
okay,
can,
yes, sir.
we are not doing sum, we are doing weighted sum.
Yes, sir. Got
We
it.
have weights, right? So basically, depending upon the number of filters, you can make with the 1 cross 1 convolution, you can make this 27 cross 27 cross 256 to 27 cross 27 cross uh, 128. So you can reduce the number of channels over there. Extracting. So basically, I am extracting features from all these uh, 1 pixel of all the channels and then creating 57 such features. So it's basically creating a fully connected layer over this one. You can think it of like that. Uh, a certain pixel 1 cross 1 convolution will look like all the pixels of all the first pixels of this image and all the first pixels of the resulting image will be fully connected in that manner, right? That's how 1 cross 1 convolution will look like. Basically, it is used for reducing the number of uh, dimension across the channels and extracting features from them. It also reduces the amount of size of the thing, right? That's why it
No,
is
taking the only one means it is losing the
not
other
only
things,
one.
right?
We will be doing the same thing with all the pixels,
Uh-huh.
right? Not only this first one. This first one will result in this first pixel,
What
and the second
advantage
pixel
we get? Now we are
we are
doing for
doing a
all the
weighted
pixel
sum
means
over channels. We
over
are
channels, but still we will
uh,
be having 27 cross 27 cross 256, right? Because we are
but
doing it
we are
for all the pixels, so it is
uh,
27 cross 27, and we are doing for all the channels.
this depth channel will reduce, right?
All channels means
Depending
if
upon
you
the number of filters, depending upon if you are using the three kernels, the output size will be 3, right?
Mm, mm, mm.
We are reducing not across the height and width, not across the spatial dimension, but we are reducing across the channel dimension.
I got confused because we said initially 1 cross 1 convolution means we are taking in all channels. That is the starting point of 1 cross 1 convolution.
Yeah, we are taking all channels.
Then how it get reduced?
So, okay, for one kernel, you take all channels and do a weighted sum to print the first value.
Okay.
So, and then in the second kernel, you go with the second value.
Okay, the channels will get reduced. Then how come? Then it should be only one channel, right? At the end, how come it becomes?
Based upon the number of filters.
Okay.
If you
Based
are
upon the
using
filter. Okay, it is based upon the filter. You mean? Okay.
if you are using 5 filters, you will have same size but 5 depth. So the
Is,
number of filters will affect the output size, even if it is 1 cross 1 convolution.
is this an example of 3D convolution? Because
This is true. Oh,
then
we are
effectively
doing 2D convolution only.
no, but like it is taking considering all the channels at once, right? And we are
All convolution will consider all the channels at once. That's what we discussed here, right? Even this 11 cross 11 convolution will consider all these channels to give
yes,
one
but
value.
the effective size of the kernel is like 1 cross 1 cross like 256 in this case. No? That's
But
why
so
it is
2D, okay. Let's say let's differentiate between 1D convolution, 2D convolution, and 3D convolution, right? In a 1D convolution, the kernel moves only in one direction. So here, so you have only one element. So if you are using a in a 1D, if you are doing 1D convolution in this image, you can do convolution with the, if you are so the dimension is 3, the kernel will look like this. The kernel will have a shape of this image 3, and then it moves in this direction. So first this 3 will be taken, and the second 3 things will be taken, and this 3 will be taken, and this 3 will be taken. Right? That's how a 1D convolution look like. Okay, you move in one direction. But a 2D convolution, you move in this direction and also in this direction. So a 1D convolution of size 3 will include this, if you are moving in this horizontal direction, it doesn't have three values. It has 3 into the height dimension also. The kernel will have 3 into the height dimension also. If you are doing only 1D convolution along this one image. But in a 2D convolution, you will move in two directions, but the kernel having will be extended along the third dimension also fully. Just like a 1D kernel of size 3 will extend along the height direction, whether it is not moving, a 2D convolution will have these two things and it will extend along the third dimension in the direction which is not moving. But a 3D convolution, so if you are doing a 3D convolution over here, you will have only 9 parameters over here and this will move in this direction and also in the back direction. That's how a 3D convolution will look like. So we are doing 2D convolutions only here. That's why it's 1 cross 1 cross 256. The size of the kernel. The size of the kernel will be 1 cross 1 cross 256. And the output size will be based upon the number of filters. So the size of the kernel, this is actually the size of the kernel, right? Here the size of the kernel, one kernel is this much. And this is the bias for that particular kernel. And we have 96 such kernels here producing 96 such images, feature maps. Okay. If for a 1 cross 1 kernel, depending upon the number of output channels or the uh, number of filters used. Here also, what is the kernel size? We move along two directions, right? But you should understand that the kernel extends to the third direction. The size of the kernel will take into all account of all third along this direction to create one image. And it does the same thing with different kernels to create individual images, right? Let me check if I
In
could
this
get
in
your.
this in this in this picture, yes means s equal to some number is there, which is
That is
tried,
tried.
isn't it? That is
Yes,
tried, right?
yes,
Okay.
yes, yes.
Okay.
Just a minute.
Yes, so that clears my question. Thank you.
Levin, is it possible to
Hmm.
show all this architecture, if, like you have shown in the previous sessions, right? You have gone to some website wherein these things are visually seen. These
Hmm.
architectures, do you have something like that to show us? Because these
Yeah,
architectures have distinct difference. The slide is covering those distinct difference, but if we see it, no, then maybe it can go and stay for a bit longer time, and the understanding will also be more easier.
hmm. So
Maybe if not
let me
this
let me.
session, maybe the coming session. This is just a
Yeah,
request.
yeah, yeah. Uh, let's first familiarize this 2D convolution. Hmm. couldn't get such. Okay, okay, maybe I'll bring in those visualization for the next session. Mm, Now let's continue with this one. So, what try to understand the idea that the convolution kernel uh, will have spread along the non-moving dimension also, right? So, one kernel will span across the non-moving dimension because otherwise it will be only moving across this image. It won't. 2D convolution shouldn't move across the third dimension, right? So, how do we connect the kernels to the third dimension? The kernel size will expand to the third dimension also. Okay. Okay. So now let's go back to this one. So AlexNet, the basic idea is using bigger kernels at the initial stages, reducing that, and then finally having this one. Here the size reduction happens through striding, right? Here the use of max pooling is not. And then the idea is AlexNet uses this GPU parallelism because of this convolutional architecture. The convolutions happens in parallelly when you use GPU, right? This matrix multiplications that uses uh, and then this VGG16 used max pooling to reduce the size, right? And that is the, and you can see the size, homogeneous architecture, which means the same size across these blocks. So that is one thing that it introduced. And the resonant residual connections is the main thing that it introduced.
Here the first two VGG and the one before Alex. What
Huh.
is the is there any difference of reducing basically size reduction, right? One we
Hmm.
use max pooling, the other one using stride.
Hmm.
What is the advantage of one above the other, or what is the disadvantage? Using
Reduced
stride,
number
what
of
happens?
parameters.
Using pooling, what happens?
So if you pool your image size actually, so using stride also you can reduce the image size, right?
Yeah, we all
Uh,
understand what is striding, what is pooling, right? But in the
huh.
context of this architecture, because people have formed it before, people have thought about it, people have gone
What
this way
so
as well.
is
What
your
is
question is
the
what difference does it make in terms of efficiency?
Yeah, there will be some differences on the efficiency. Some things will be efficient on some features of the picture. Something will be
Hmm.
efficient on maybe pooling is efficient on some kind of a picture. Maybe it is. I'm just want to maybe some insight you can throw on. When I do size reduction using pooling, how it is, what kind of specific areas it can address, what kind of other areas, specific areas the striding will address. Maybe that is the question.
Okay, so using striding actually complicates the architectures. So you see, when you use stride, you won't be able to. So you can like predict like how the size will. It depends upon. So the size reduction is depends upon the kernel size and the slide size, the image size. All those factors determine the image size reduction, right? So the use of kernel and everything has to be very perfect. But here, what you can easily do is here the use of kernel sizes. You can pick any kernel size and don't worry about how I am going to reduce it to the next size. You can always do a max pooling to get a half the size if you are doing using a two size of kernel. So constructing the architecture was simpler. Where here constructing the architecture, you have to compute every output size and so on, right? And also, what this is doing is having same amount of the sizes. You see the uh, architecture was not varying as this one to give the same efficiency. Right? That is one thing that this VGT introduced. So it's not like there is very well known or predictable advantage over there. In deep learning, most of the things are like experimented and trained out. So one thing that this one does is reduction in the size of parameters that might you can think of. That is one thing. It could do with the reduced set of parameters also. That is one thing about this architecture, right? But in terms of how that is different from, you can also use pooling over here instead of striding. It will also work. In the same election architecture, this is like historical architectures, right? But you can try instead of doing a stride over here, you can use pooling with the same size. That will also work, right? So this is like we are studying research papers upon what worked well to get ideas about the architectures. And one more thing is we have pre-trained models of this particular exact architectures. So we can fine tune when we do this transfer learning. That's why we used to learn this famous CNN architecture, right? We have pre-trained weights. That is one advantage of using pre-trained architectures for tasks. Other than that, it's upon, as I said, right, everything started with the ImageNet challenge. So it was given us a challenge, and whichever models broke the previous one is what we are actually studying, right? VG16 was chosen to be in this slide because it broke the SelectNet's record in a next year challenge. That's how it works, right? There is no direct predictable relationship between those things. So the thing about deep learning is most of the things are experimentally proven rather than theoretically proven. So you cannot say so, but you can get the intuition about things. So try to learn deep learning with the intuition rather than exact theoretical uh, proving like mathematics or linear algebra like that. You will get the intuition of why this might work and why this is better. Okay.
Thank you. Thank you.
Yeah. And here also, as we see in all these chapters, we always start with some intuition rather than providing direct uh, proof that this works, right? Here also, we just introduced that it introduced ReLU and it worked. It broke the challenge, so that's why ReLU got famous. It won the challenge and it got famous. People thought, okay, ReLU works fine. Then they used and found it useful. Other research papers supported that, and it went on. And it was simple to implement, so people went for that. And then here in the ResNet, we introduced the skip connection. So this residual. So when you try to increase this number of layers, it goes too deep, and then the network would saturate. Like propagation of gradients also will be a problem. Sometimes that propagation die, there are problems like vanishing gradients when you train a neural network and all. The gradients might stop and vanish at some point because you are doing multiplication, right? So assume you are taking a number less than 1 and multiplying many times, it will become even smaller, right? So 1.1 times 1.1, zero point 0.1 times zero point 0.1 will be 0.001, right? So when you multiply, this kind of numbers tend to vanish also sometimes while you do repeated multiplication factors. So that is one problem called vanishing gradient problems. That happens when you increase the number of layers or the depth along the axis. So that's why this skip connections provided the way to bypass the gradients in some manner by introducing the skip connections. So that worked well again, and then it became ResNet architecture. And here the idea is why don't we use different convolution kernels at the same time? Why we have to choose only one convolution layer? So that's why the intuition through this one. And then again it worked well. And you see this one, the reasoning that are actually provided here are not very uh, recent. So things like bottleneck. So we think that to do this, to make the parallel computation feasibly faster, use one as a bottleneck layer to perform dimensionality reduction, right? So dimensionality reduction means the reducing the number of batch size so that you can do parallel computation. That is one idea about this. So here, this is why it was used. It has a less parameter count because of this one cross one convolution. So this one cross one convolution is the key thing here in doing the parameter reduction over there, right? So you are doing one cross one convolution, max pooling, and also one not one convolution to do this one. So this one cross one convolution reduces the number of parameters in the next layer by reducing the depth size. So you see this, why that is needed, the number of layers. So depth concatenation is happening here, right? Depth concatenation means, so this one's output, assume we are using in a 3x3 kernel, we are using like 5 filters. There will be 5 images here. If you are using 5 filters over here, there will be 5 images. So if the number of filters is same across everything, you will have 25. Assume 5, 5, 5, and here it will be 25 filters that we have to use, right? So before passing into that, if you use one plus one convolution, we can actually reduce the number of output dimensions. Since we are concatenating 4 outputs, right? We can reduce the number of inputs in such a way that we are reducing the number of outputs. To give you an idea, yes.
So before concatenating the different outputs, feature maps of these parallel pipelines, we do have to make sure that their output dimensions are same, right?
You can use same padding, right?
Yeah, we have to play with padding and stride to make sure
Yeah,
that the output dimension
there is
remains
this
same.
standard padding. So there are like two standard padding techniques used. One is valid padding, which is no padding, and same padding adjusts the padding so that the output size is preserved. So we'll be using same padding across these ones.
If we use same padding, then let's say the 3x3 output size will be different at 5x5. So
No, no, no. Same padding doesn't mean same number of padding. Same padding means uh, the output will be same as the input size.
okay, okay, got
Not
it.
okay.
The
Same
one that
padding is
was
the
taught in
term
week
that
three,
is
right?
used. Huh?
The thing that was taught in week three, same
Uh,
padding. I thought the same padding across the
Not same
whole
padding
animation.
across this one, same padding in each of this one, so that
Yeah,
this size will be same as the input size.
got it.
Okay. Okay then. So that is the idea about this inception module, and this inception module is used in this layer in the Google Net architecture. So this module is, you can consider this whole module as one layer. So that's it's this whole thing is composed of this inception modules. That's how this works. So you see this one, this is the inception module. These are the inception modules that are used. So in the initial layers, there were similar convolutions and some normalization layers also introduced. And then the main thing is about this one, which is the inception module. So this whole thing is an inception module, right? And after some inception modules, a max pooling and some inception max pooling and things like that. Then finally, and also dropout layer also introduced. So these people introduced these different concepts, and then finally with this one, we don't need to use. So we have trained everything, and then we don't have to retrain for each specific task. We can use transfer learning. So transfer learning, we in CNNs we do different approaches. For CNN, what are the different approaches we do for transfer learning is pre-trained convolutional base or a fixed feature extractor. And then this is one. We'll remove the classifier head. The classifier head usually denotes the last layer or the uh, so fully connected layers. So we train the fully connected layers. That is what we call a classifier head, right? So it will be like that. So there are different types of transfer learning. It depends upon how many layers are going to reach, right? So that is what we call
Sir,
freezing of the weights.
what would be the example of pre-trained convolution base?
Uh, Take any of this architecture. So there are like these architectures have been trained in ImageNet data, right? So this would be the feature extracted base, the convolutional part. You remove these layers, which means remove this layer means change the weight, like reset the weights or something like that. And in the next training process, when we are training it with our data, we won't be updating these weights. We will fix these weights and update only these weights, right? So that is something we do. That is the so then this all convolutional weights that were previously trained on the image and data acts as feature extractor. So what you get as the result of this one is set of features, right? Feature maps. So that so we consider those as features and use fully connected layers like a multi-layer perceptron, right? So it's essentially training a multi-layer perceptron with image data using the pre-trained convolutional neural network base as a feature extractor. After flattening, what you will get is a set of features, right? So that's why we call this as a feature extractor part.
Okay, sir.
This feature extractor is what is
Huh.
bugging me a little bit, because normally when we were doing this MLP and all, this feature extraction, we try to study about the feature from the database and then
Yeah,
say this
because
feature.
yeah,
I will just finish my question. Just I'll take maybe 10 15 seconds. Yeah, we will try to see its relation to whatever it is, whether numerical or categorical. See its relation to the actual output, classified output or numerical output, and then see this feature is important. That's what we say. Here
hmm,
we have weights, and the
hmm,
model try to understand the weights over various iteration, right? Then
yes,
still, why how we say this is because weights are there here, means
huh,
there are learning happening on the
yes,
weights. So just I want to bit how we say this is a feature extraction. This just I
okay,
want
yeah,
to
yeah, okay, okay. So just okay, this architecture is there, whole neural net, the convolutional neural net. We train this on a ImageNet data, right? Which means all the weights will be learned at that time. So ImageNet is a classification data, right? It has like 20,000 classes and all with millions of images, so on. Okay. And now we train this, and all these weights will be updated during the training process, and it gives a better performance, which is good for that particular task. Okay. Assume, okay, during inference, when we are predicting, right? We don't update the weights, right? When we are predicting, we don't update the weights. We compute the outputs. When predicting, this image goes through this one and it flattens into a set of bunch of neurons. Finally, after the convolution, the flattened layer would be here. then it goes through the fully connected layers, right? So in a traditional MLP, the input layers are the features, correct? So you can assume that whatever this whole thing is basically some mathematical function. The convolution is some mathematical function, right? And you can represent this whole thing as some transformation. So you transform the inputs and to get some n values, and your these layers use those values to predict the class, right? So at inference time, this whole function is predicting a set of values which you can assume this part of the neural network is trying to classify, right? So that is why these are called features. So once trained, these are fixed values. Once training is completed, these are just fixed values, which are basically some transformations. So assume you have a simple data set, you can create complex features by doing x, multiplying x and y, you get a new feature, right? Basically, these values that we get are some mathematical operation that has been done on this image. So that could mean those are also features which this network is using, right? So the previous layer, so we call this feature map, right? Why? Because from every layer, what we are extracting or the output, what we are getting from the previous layer of a convolution layer is called feature. It's called feature map in convolution because we are arranging them in this image-like fashion, right? But once it comes here, it becomes plain features, which a multi-layer perceptron is trying to use for doing the classification. So, as you said, in the previous MLP, you manually extract features, right? Whatever value is, you do feature selection, you do feature engineering, you compute complex features manually sometimes. Through that, you do some mathematical transformations. For example, if date of birth is given, you might take age as a feature. You compute with the current date, you take age as a feature and pass it to the neural network or some machine learning model, right? Similarly, that this kind of extract certain features, which is doing this. Now we come to the why does that features work? Usually, it's a classification task, and these weights are these features, this set of features that this whole thing is extracting, is giving a good. Uh, these features are kind of proven to be good for one classification task. So then these features can also sometimes be used for other tasks also, right? So some different classification also. These set of features that has been trained in ImageNet was performing well in that uh, task. So we can use that pre-trained features. This is just a mathematical function which converts an image to a set of values, right? And then this network uses that features to learn. Here we can update. So when you freeze and do the training, this just becomes a fixed mathematical function that kind of extracts some features which is learned by the ImageNet classification task. We did training for that. These weights are fixed at that point. So when we do transfer learning, we only change these weights. We don't update these weights, right? So then this whole thing just becomes a simple mathematical equation, right? That's why we call them as features. You do some transformation to the input pixels and you get some values. Those are features. Because now only learnable part is this one to which the previous layer's output acts as the input features. Okay.
Yeah, thank you. Only thing is, I feel this I last session also we had the similar discussion. It's see here we are taking pixel by pixel and then try to map it. Here the entire thing is based on the pixel value.
Yes.
but we were discussing like how we identify an image in our mind. It is the entire image. I think for the image processing, entire image might be, because we don't do this much complex transformation, doesn't happen in our mind.
Yeah.
We
So
see a
how
person,
our mind,
we remember a person.
so
We
how our
remember
mind
this,
works is a whole
like
lot of different theory and
when we
all.
see a dog, we see everywhere, we identify dog as a dog. We
Yes.
wherever it is in our, when the eye see a dog or a cat, in whatever world it is, or whatever place it is in a zoo, or it is in a open wild, or it is in my house, we identify it as a dog. Just because we are going to a pixel and then trying pixel value and then trying to transform it, map it, and then it becomes too complex than how we do a
Yeah.
classification in our mind.
Yeah.
If we understand that, that would be the best way of identifying the image, more easier and more faster, more quicker. Maybe I don't know how this is happening inside, but we had the similar discussion last time also.
Okay. Yeah. So that is what is described in this transfer learning process, right? So here we freeze weights of the base layers, removing the original classifier and add the system. So this is one strategy. Then as a fine tuner, which means we uh, feature extractor. This idea is freezing weights. So the previous frozen weights acts as those layers which weights are frozen acts as a feature extractor, and we. So the idea is, so in this model where we are freezing some weights and training the remaining. So the feature extractor acts as a uh, some kind of fixed mathematical function which gives you certain features, and you train a whole new neural network on top of it. So the remaining layers is basically a new neural network part over there, right? Randomly initialized the neural network part, starting training from scratch. So that part will start training from scratch. So this is one way of transfer learning. A fine tuning is you don't freeze, but you initialize the weights with the pre-trained weights. You don't do random initialization. You initialize with the pre-trained weights, and then you can do unfreezing with different levels. So you can unfreeze the entire thing, or top view, or something like that. You can whatever you can unfreeze. You can fix some of the weights, and you can not fix some of the weights. That depends upon how you want to pre-train. So the initialization will be based on the pre-trained weights. You don't do random initialization. So start from the pre-trained weights, and then that is the idea of this fine tuning. Feature extraction, you use the fixed weights to give you the features, and then train a whole new neural network. Sometimes it's not, sometimes these kind of methodologies were also used. You need not always use uh, fully connected networks. So as I said, this gives you a certain list of features. You can try out different machine learning algorithms also on top of that. Like you can have some logistic regression on top of that, and you can have SVM on top of those features. You can try a lot of different things, right? So that is also actually done sometimes. So whatever you create, compare these are the features, and you can train basically any kind of machine learning model with that features. Those are experimental. But when we talk about fully neural networks, uh, we do fully connected layers usually.
This transfer learning is only for this CNN, for image
No, no,
classification only, or
no,
any
no.
LLMs we can use this
All LLMs,
methodology.
all neural network architectures, you can use this transfer learning, fine tuning, and the LLMs also. actually do fine tuning in that. We can also fine tune LLMs. So the methods will be different. Architecture, since the architecture is different, fine tuning methodology will be different. That is the idea. But
But the
idea is you
concept
are
still remains the same. Transfer
ah,
learning is a concept. We have not learned this when we are doing the MLP or anywhere. Only
yes,
now
yes.
it is being introduced to us. So that's why I'm asking this question: is it only purely for the image, or it is for globally for all machine learning? It's a machine
Eh,
learning concept.
Transfer learning is actually a machine learning concept, but actually it is more used in deep learning rather than machine learning because machine learning models can be trained from scratch usually, right? So depending on the size. So, but in these deep learning models, so training this in ImageNet data will take a lot of time. So, but we have learned something from that. So, can we use that world knowledge to do some other task? Is the idea of using transfer learning. In this kind of unstructured data only, learning something useful. So, are the features something that you have learned from doing that task helps in doing other tasks? So mostly you will hear deep transfer learning in this deep learning context rather than the machine learning context, right? So as a feature extractor, you can train your own new classifier. As I said, you can original classifier head you can and you can add a new classifier which can be a neural network, fully connected network, or some other things, right? So in LLM case, yeah, this feature extractor is something called as embeddings. We call them as sentence embeddings or word embeddings. You put in a paragraph of text and you get an output, which so it will be trained for some task, but we'll take last layer like this. The feature extracted, I stopped with the convolution layer, like so in the language models, there are encoding models are there, which will give you a set of embeddings, set of feature values, which represents that particular text or a paragraph or a sentence. And we can train certain machine learning models on top of those things. So those are also being experimented. So this is one way of doing transfer learning, using the pre-trained certain layers as the feature extractor. Why feature extractors are needed? Because we are doing with unstructured data, right? So this feature extractor provide us with the very structured n number of values, which represents that whole unstructured data. So that's why this feature extracted way of doing transfer learning is also there. Fine tuning, sometimes this method not perform very well for our particular task. Maybe for the same task with different classification. So there are like the classification task, maybe it will work well. But sometimes our task will be different, our data set will be totally different. Then we go for this fine tuning methodology where we train like unfreeze certain amount of weights and then retrain the whole network again, right? Whole network or the certain part of the network again. This is what we call as fine tuning, right? This is
Sir,
one.
can you please explain in simpler term how fine tuner is different from feature extractor?
Okay. In feature extractor, we use the convolutional part to extract some linear features, some features, and then we train a custom classification model on top of that features. So this will be this architecture will be only used for inference. We are not going to change any of these weights. The classification weights, we are not going this convolutional weights. We are not going to change this one. Assume in a VGG, this much will be feature extractor. Okay, so you can assume that this is a separate part. We just take the output of these values and replace this whole thing with some machine learning classification algorithm or whatever algorithm you have, right? So this will be a fixed function in a feature extracted mode. This whole thing will be a fixed function. But in the fine tuning mode, you initialize, as I said, you don't have, you replace this whole thing in a feature extracted mode, right? you retrain a whole new thing. But in a fine tuning mode, you initialize all this thing, and maybe in the last layer, depending upon the softmax size, you might want to change the last layer, right? So depending upon the number of classes, you change this layer, and then all these layers will be initialized with the original weights, and then you start training from that original pre-trained weights. So fine tuning is you start from the original weights. You can freeze up to this layer, initial this, you can freeze, unfreeze the whole thing, or you can change the weights of the whole thing, or you can choose to change the weight of only this many things. So you can choose, that depends upon how different is your task from the original task. So sometimes if the task that you are training and the original task is similar, you might want to just unfreeze these things and use the original weights starting from here. But if your task is too different, you might want to train all your weights. So you start with the value. The idea is you start with initialize with the pre-trained weights and then do a whole training is fine tuning. But in a feature extractor, you don't even train or do anything. You just use this thing to get a set of features and then use your own classifier. All right? That is the idea. Okay. Huh. These are some ideas about things. Uh, yeah, why this works and some intuition about that. Then there is this, they are introducing this unit and other stuff. Okay, so as I said about the segmentation models, they were like pre-trained. Segmentation has this whole new architecture of CNN called unit. So unit also involves certain operation called deconvolution, which is like uh, so convolution usually does shrinking of the image size, right? When you convolve with the stride, but when you convolve with the stride in deconvolution, it will increase the size of the image. So it is something unit will kind of decrease the size by repeated convolution and then expand the size back like that. So that kind of architecture is a separate architecture altogether. Uh, so I think that is discussed also in week 4. Right, introduction. So mostly this kind of architecture is used in image segmentation tasks. Uh, get the picture. I think visual representation is not here, I guess, but I think you can get the. Um, this will look something like this, right? You do convolution here to reduce the size, and also after going to the last level, you do deconvolution to get the original image back. And you will also have skip connection between the corresponding layers. Skip connections will be also there. So inputs to this layer will be the first layer and this layer. That's why it is kind of arranged like a U. That's it's called UNet. The inputs to this layer will be the original layer of that size, and this uh, decoded uh, layer. Both will combine together and produce this output like that. So this U whole unit architecture looks like that. Okay. So that's the basic idea about that. That is usually used for segmentation. So the basic idea is same. Here, if you are implementing using PyTorch, I think you can use this. Uh, okay. Here, unit architecture, how we are building the architecture. So down here, the reconvolution is also transposed thing. So basically, this is also called as deconvolution, right? So we are using this layer, but in convolution, you use the conv layer like that, right? Okay, so that's about the architecture. So going through this code, understanding this code can be sometimes very tedious, but once you understand what each layer does, so when you should what you should do is take a look about each layer and first study about each layer once. So once you understand each layers, then you will be able to easily construct a custom neural network on top of it, right? So everything is about modules. We construct a neural networks, complicated neural networks with modules. So certain block of layers, we combine it with using sequential or doing a concatenation like ImageNet doing parallel thing and concatenating it like a inception module and different sort of things are there. But at the core, it's all mathematical functions organized in a linear fashion. That's how you construct a right.
Sir, is this unit is a older architecture or modern architecture
Modern
for
only. It
image
is actually
segmentation?
unit is used in mostly till to date image segmentation unit is used, right?
Okay, sir.
Unit is a very standard architecture. It's kind of proven for these kind of tasks. Even in so there are like certain models called diffusion models. Uh, Units are used as one part of those diffusion models for reconstructing image back. So there is something called as latent diffusion models, which are kind of the image generation models. So those also uses units to reconstruct image back from encoding. So it compresses down the image units, right? So it reduces to the image, and then it does processing there, and then it reconstructs back. This kind of compressing and reconstruction task unit is most popularly used. This is modern only, right? Okay. Yeah. Anything else you want to ask? If you want me to describe anything in particular, I will go on that part.
So someone has asked question in chat.
How Google inception model different sizes could be concatenated. So the inception kernel size are different, not the output size, right? So I think we could construct a inception module. Let's try a new notebook. Let's try constructing an inception module with PyTorch. Let's take the PyTorch stuffs. This much only we need. First one, right? So this is how you create a PyTorch module, right? Um, then we will set self. So in a inception module, what are the things that we need? these things, right? So convolution 5, the sizes also we need, right? So let's take the number of kernels uh, in this each of these ones. Okay. Um, it's not taking channels and out channels. Okay. Number of 3x3 channels, number of 5x5 channels, number of 3x3 channels, then number of um, 1x1 channels. Then there is let's just keep this to the side. Ah, okay. So first we have to reduce this, right? So here there is the input channels. Number of input channels will be there. But first you have to reduce this one, right? Which means let's say this one as mm, let's use same amount of kernels in this one. So this one and this one will have the same amount of kernels. Let's take that idea. So that will be like that. So this one plus one path, mm, this one, and this can be we can use same number of filters in this and this also. All this will be same, and these two will be number of filters over here and number of filters over here will be same. Number of filters in this one and number of filters in this one will be same. We are going by that idea, so we have this ones. So we can create the layers itself, right? Self dot run one x1, right? So this part will be the run one part, or we can call that uh, part one, part one is equal to. So in the sequential, we can add these two layers. Mm, yeah, and activation. So this is, let's say this is the uh, first channel, 5 cross 5 channel. Kernel size is 5, right? Then we add ReLU, then one more convolution. This would be, we don't need number of channels is equal to 5. Whatever is coming out of there will be the same, and we'll be having same for the next thing also. This path will have that many number of channels throughout. If that's it. So this is the
Sir,
part
by
one.
looking at image, how did we decide that this is convolutional 2D, not 1D or 3D?
Usually for images, we do convolution 2D. So one-dimensional convolution is usually done in sentence classification or sentence when you process sentences, and there we can use 1D convolution. So since image is a 2D data, we use 2D convolution. We don't use
Okay, sir.
3D or 1D convolution usually in images. In 3D convolutions are used in videos. where you have a time axis also. So then their 3D convolution is used. Right? Okay. Then self-drug part 2 sequential, and here we can use the same thing. So the part 3 will have just this one. So only this and ReLU. And then the part 4 will have max pooling also. I think that is doing that. That is fine. So we have 4 parts. So we'll just initialize everything in this one. Then we'll go to the forward part. We have to define this one. Right? So here we do concatenation along this one. So all these things we concatenate. Okay. So now let's talk about the output sizes. So have we really worked on that part? Do all these sizes matches? Let's verify that one. So here the convolution, uh, what is the padding that we have used? Okay, what is the padding we have used? So what we can do is we can use the same padding over here. So I'll use same padding, right? Uh, let's see one more thing. Here, the max pooling 3D is 3 cross 3 is happening, which means here the size is reduced, right? So what do we do here? Mm, mm. Okay, so the how does that is being? Mm, mm.
So looks like we will have
Okay,
to create
okay,
three.
okay, okay. Max pooling 2D. Actually, this max pooling 2D need not reduce the size. Why is that? So usually in max pooling layer also goes in strides, right? So here the stride is set to be 1. So usually when you do, this is how it ensures that the size is actually not reduced. So by default, what will be the stride? The stride will be the kernel size, since whatever you are giving here. So the previous things that we saw when the max pooling layer reduces the size, a 2 cross 2 max pooling kernel will reduce the size of the image if the stride is 2. So it's a 2 cross 2 kernel. It takes the first two 4 values and gives one value, and the stride will be 2. It goes and select the next 4 values. If stride is 1, essentially the output will, what will be the output you will get? The same output, right? So that is why here, instead of using the kernel size, if you are using the default in a pooling layer, the default stride will be the kernel size. But that is not usually true in this one. Here the stride is usually set as a number. Usually it will be one kind of that. The number of how you move, right? But here the side for pooling layers, usually if you want to reduce size, that is the default case for where pooling is used. So there this value will be set to the kernel size, whatever size that you give. So if you use 3 plus 3 kernel, it reduces by 3. But if you set the value side to 1, it will do it will remain the same. That's the idea. Here also we can use same padding. I think no. Okay. So here the padding size. How do we decide the padding size? Yes. If the kernel size is 3 and the stride is 1, to get the same size, we use padding of 1. If kernel size is 5 and the stride is 1, we use a padding of 2 to get the same size. So it's like manual calculations required over pooling layers in case of padding. So this ensures that size is conserved. So basically we are manually doing the same padding and preserving the size over here. Here we can use same padding. Okay. So this now makes sure that all these layers will have same size, input size.
And sir,
So
what
next,
about cooling? Don't we have to pass cooling argument somewhere?
uh, pooling the size argument.
So pooling, sir, I think by default, does it take true or false, or is it does it take the numeric value?
This is pooling layer, right? This actually does pooling.
Oh, okay, yes, sir, yes, sir, yeah, max pool, yes, yes, sir, yeah.
Okay. Okay. Now let's try with the simple tensor. We'll first initialize this one. Instruction equal to this one. I'm just initializing with these values. Okay. Then let's take input r choice x and create a uh, random one image of uh, 3 times 23 or 24. That's how it works. Okay. Now let's run this. You can see how it is coming. So 16,
So
15,
in the previous
16.
code, I have one doubt.
Huh.
So, sir, in this, basically, we are going to create as many numbers of convolution like so we have like 5 cross 5, 3 cross 6, whatever convolution layer and pooling, and then
Hmm.
lastly the forward. So will that be the all, or is that my understanding right? I mean, we have to create for each convolution max, or if there is pooling, and then finally the
No,
forward.
no, no.
Yes,
Pooling is only there in this part. Here pooling is not there.
in one
Only in
cross
this
one, right,
line.
sir?
This only in the 1 cross 1 part there is pooling. This part 4.
Okay, sir. But sir, in one cross one, there are towards left side as well. We have 1 cross 1, right? So how are we
Yeah, this
differentiating
is
this with pooling and without pooling?
how are we differentiating it? This is part 3 without pooling. The same thing with pooling is part 4.
Oh, okay, sir. Yeah,
Here,
understood.
when we pass the inception argument, we only pass only for the three paths.
Yeah, you can configure like the different number of kernels for here, everything you can do. Now I simplified it so that I have same number of filters in one part. So the number of filters you can change. You can customize this according to your needs. So I just use simple so that you can use some set of number of things. So here it is like 16 is mentioned, right? So if we change it to 32, then you can see this one changes. 16 plus 16. Uh, so this is the number of output filters, right? So the number of filters that are coming out here is, yeah, out channels is this one. So 16 plus 16 and one more 16 and 32. How will it came to be 80? Okay. Okay. Uh,
Is it because of the fourth one? We are calculating only three. There is four
Uh,
paths.
yeah, fourth part. Yeah, the thing is, this will have this output channels, and this will be also same. Okay, so it is like 16 into 3 plus 32.
Then
16 into 3 plus 32. It is 80. So 16 for the part 1, part 2, and sorry, part 1, part 3, and part 4. And this one, we will have 64, sorry, 32. So 16 into 3 plus 32 output channels. That is what we get to see. Okay.
say for example, for okay, this is not for the understanding. In the exam, we will be given with three arguments for a for the inception module with four paths, and then
It can be
we'll give.
customized. As I said,
Mhm.
it need not be. So here I am having same number of filters here and here, but you can customize that. You can customize like uh, 5 cross 5 1, which says number of filters present in this one or this one, and the number of filters present in this one can you can say 5 n 5 cross 5 5 cross 5 2, which actually says in this part. In this part, how many terminals are there? You can customize these numbers based on that. So here I can put this to be 1, output channels will be 1, and that same will be here as input, and this will be 2. You can customize if you want more arguments, right? If you want to customize, you can. So now this I can also pass a different set of, so this will be there. The first, initially it will have inner input channels, and then this will be the Cycross one second part of the part. Number of channels there I can configure here now. Mm, yes, so I can have some 8, I can have this. So essentially what will happen? You see output layer, keyword argument, okay, I haven't run that cell yet. Huh. You can see that, right? Even though inside here there are 16 filters, out in the output it is got reduced. We reduced it to 8. So you can add arguments for those however you wish. Everything is customizable. You just have the certain framework, but in the actual Google Net architecture, you see the sizes are fixed. I think these sizes denotes the individual things. These individual 6 convolution blocks are there, right? 1, 2, 3, 4, 5, 6, and I think these uh, actually number of filters in these 6 convolution blocks. You can configure that. Each of these convolution blocks, you can set the number of filters, and then the output layer filters or the number of filters from all these layers will be concatenated together. Okay, is that clear?
Sir, what kind of question will be asked from this inception module in exam?
There can be questions like, uh, so as I said, the computing the output size can be a question, right? So anything depends. It can be anything, right? If you can do some computation, if you know how things work, how basic convolution work, how then you can answer pretty much anything about the inception model also, right? How
Regardless
one
of
cross
this
one.
architecture, whether it's the inception module or any other, the formula remains same, right? To compute the output
Yes,
size, which we have seen earlier,
yeah.
like input
So
size minus
the
delta.
elemental items are Con 2D, Max Pool. These are the elemental things. So I constructed those from these elemental layers, right? Convolution 2D is a elemental layer which performs the convolution operation. And then similarly, you have these fully connected layers, which is like a linear layer. And then you have activation functions that defines altogether, things like that. So this core elemental things remains the same. The principles remains the same. How we compose them is the only thing that we learn after we learn the core basic architecture. In RNN also, you design architecture with the RNN uh, uh, module. Layer will be there, one kind of unit will be there. So with the core layer, you will be uh, adding, creating complex neural networks. Okay.
Okay, sir. And another question, for fully connected layers, do we have extra biases?
Yeah, usually
Like,
for every biases will be there by for everyone, every layers. Convolution also will have biases. Fully connected will also have biases. By default, it will have. I think there are like ways in which, yeah, this argument will be there. Bias equal to bool. You can by default it will be true, which means it will have biases. You can make this false to not have biases.
okay, sir. So by default, it has one bias each layer, right?
Yeah. Bias will be there.
Okay.
Okay. Yeah. So any other doubts is there? Oh, okay then. I think we can stop session for today. Oh, thank you everyone.
Thank you,
Thank
sir.
you.
Sir, if you can please get the more questions shared.
Yeah. Okay. In the coming sessions, I will ask the TAs to present this kind of problem solving sessions. Okay.
Yeah, and one more thing, if there is any pictorial representation of mainly this convolution, no? If we take an image, how the image transforms, because we are doing everything together.
I
Sorry,
suggest for
sorry,
now,
inception. Sorry, not convolution.
uh,
The inception. Inception.
yeah,
We do
I'm not
everything
sure.
together and
Yeah,
concatenate. So, image normally, if we use the CNN, how it goes, and we use the inception, how it what happens. Maybe that gives because the overall story is
you
very
want
very
the
simple.
output. You want to see the output.
Yeah, same image. I do a normal CNN. I do an inception. What happens to the
So the
image? How
output will be similar. So the output will be just a set of feature maps. Will be output will be same in both cases.
okay.
Output is the nature of the size of the output. You see 72 cross 2 cross 24. So here you see this is the input size and this is output size. You
So
can also have a single.
when I have to use the inception, when I have to use the that question comes right because the inception looks like it is more calculation intensive, right? Because more power is required because you are doing so many things at one time. In that one layer, you do a 5 cross 5, 3 cross 3, everything in parallel you are doing. Yes.
Yes.
Convolution you do series step by step. Looks more less processor means calculation intensive, less CPU
That's
power because you do
no,
things
that's not.
series. This in parallel because I deploy 4 people. Here I deploy one person who do one by one. I'm just seeing like that. This
Yeah,
architecture looks
that's
good.
yeah. One thing. That's why we use this one cross one previously to reduce the number of sizes. The number of this one. So here see, if in a previous image, so assume there are like 256 channels, 256 channels. In a single convolution, if you are using in this layer, the input channels will be 256, right? Let's go with the calculations. So let me say compute the number of parameters. Let's compute the number of parameters that are there. Assume our input layer have 256. All right, and now let's compute this number of parameters in one convolutional layer with 5 cross 5, a single convolution layer with the 5 cross 5 size, right? And so what will be the, and in the output we have again 256. We can have, let's do this calculation, single calculation. This is the C in, and this is the C out, and here it will be cross 256 plus 1 times 256, right? So this is this much parameters. Okay. Now let's do an inception module. I'll do some simple inception module. In one part of the inception module, let's take, there we'll have these two things are there, right? So what we'll do is using the 1 cross 1 convolution, we'll reduce the number of sizes to, you can reduce it to maybe 64, right? Plus 1. And in the output size, sorry, this is the input size, right? So input size will be 256. The output size will be 64. Okay. Then in the next 5 cross 5, your input size will be 64. Okay. Then what you have times, let's say output also has 256. Let's compute how this works. You see this value? It has lesser number of parameters than the plain CNN, single
It's
convolution.
only one path, right?
Yeah. What I'm trying to say is, this is one path. So even 4 times this is roughly that size only, not very complicated,
Ah, is it? Okay.
right?
No, but the time you are doing everything parallel. Yes, same computation, but you
Ah,
do everything together, right?
yes.
Here it
Yeah,
takes
that's why
four
it gives an
one by
advantage.
one.
Yeah, here we are having different computations with the, so here this is 5 cross 5, but not everything is 5 cross 5, right? There are like 3 cross 3, 1 cross 1 also there. So
Okay.
essentially you will have
Measurement will be the
very
same.
less number of, slightly less number of parameters, but we have feature extractors that work in different sizes. 5 cross 5, we have multiple viewpoints with the same amount of computation. If you are not using 1 cross 1, you will have more parameters. But that's why this 1 cross 1 is needed to reduce the number of this one, to overall reduce the thing. You see, the other layers would be something similar to, so 3 cross 3 will be like this, and then you have two 1 cross 1s, right? So we can have 1 cross 1s. You are getting advantage of different layers with using a single thing. Is 2 into, you can have 2 into this one plus, this one plus. So what is this whole thing? Actually less than this, right?
Okay.
So that's how inception module actually kind of reduces the number of parameters in one block rather than a single convolution. As we saw that a fully connected layer has more parameters than a convolutional layer, similar to that. It might looks like we are doing many things, but the amount of computation requires is relatively less than the standard single convolution with that many things. because of this one cross one convolution. That's why actually that one cross one convolution is needed. And also, yeah, I forgot one thing. So we'll be concatenate everything, right? So to get the 256 output, we actually don't need to get output size. We'll be concatenating all those things. So we'll be in the output itself, we'll be using 64 only, as you see. Then we'll concatenate everything to get 266. 64 of this and 64 of this. And each of the 64 final outputs, the four parts, will be concatenating together to get the 256 back. So it will be much lesser than our estimated, right? Okay. So the input is 256, output is 256. Here also is that, here also the same, but less parameters in inception. Okay. I think we can stop with that.
Thank you. Thank you.
Yeah. Okay. Bro. Thank you.
Thank you, sir.